Hey everyone, I'm glad you're studying and wanting to get ready for the pre-calc final. So I have some stuff here that I hope will help you. This particular recording is going to look at a few examples of key concepts from trigonometry stuff. So some of the things that I think are really important to review is using identities to simplify and reorganize trig expressions. Another topic is solving equations. So you want to be really proficient at solving trig equations. Also, you want to be proficient at solving triangles, both just drawings, geometric drawings, and also word problems that involve triangles. And then lastly, we'll look at graphs of trig functions. I'd like you to be able to take an equation and make its graph without using your calculator. Give me a sketch. And vice versa, I'd like you to be able to see a graph of a trig function and write down its equation. So those are the things I'm going to review here first. Now, starting off with this one, using identities, it is imperative that you memorize identities. And we are, you're getting ready for the final, so time is pretty much towards the end. But oops, that's not the one I want to show you. This is the one I want to show you. This document here shows you a collection of identities that I think you should memorize before you go to calculus. So here's a whole sheet of all the different identities, and the ones that I put in yellow I think are imperative. Things that you should know and take with you when you go to calculus. You just want to know these by heart. And so there's several things here. The unit circle, that's not that big a deal, but the opposite adjacent hypotenuse and the exact value. So I encourage you to look over this sheet and make sure that you've mastered all of these identities that are yellow. You should be aware of all the other identities when you go to calculus, but if you've memorized these yellow ones, you'll probably be in good shape. And you'll be in good shape for the pre-calculus final too if you've memorized those. So that's the first thing, is getting those under your belt. But let's practice working with these identities here. All right, here we go. I have written down an expression in trigonometry, and I encourage you to pause the recording right now and simplify this on your own. Challenge yourself to make that as simple as possible. And after you've done it, then push play, and you can check against me to see how well you did. Okay, so hopefully you did that. Let's simplify. Now, there's some identities here that I'm hoping you're remembering. Sine of a negative x. It turns out that equals to negative sine x. So we're able to simplify that expression. Cosine of negative x turns out to be just cosine of x. And cosecant, I'm going to do two things here because cosecant equals 1 over sine of negative x. But sine of negative x has that same identity here. So I'm going to rewrite this sine of negative x as negative sine of x. And so we just use those identities. They're called even-odd identities. And the name of them isn't that important. But knowing this relationship is important. And so it turns out that this sign will cancel with that sign, and the negatives are going to cancel out too. So in the end, this turns out to equal just cosine x. So that long expression simplified down to something quite simple there. Here's another one. All right, here's the next one for you. Now, like I mentioned before, I encourage you to write it down. The best way to learn is to struggle with this. to really work yourself and make yourself try it and stretch yourself. So pause and solve it yourself. Take that expression and rewrite it so that it is in terms of cosine only. All right, hopefully you did. Let's see what should have come out of that. We need to use some identities here to start simplifying. These are our less user-friendly trig functions. So tangent sine x over cosine x. Cotangent is cosine x over sine x, and all of that is over cosecant, which is 1 over sine x. All right, so I'm going to transform this giant fraction in here and multiply by the reciprocal. So I'm going to have sine of x cosine x plus cosine x sine x. This is my numerator. And now I'm going to times it by the reciprocal. So I'm taking that sine x over 1, and I'm going to distribute that through. And I will get sine squared x over cosine x plus, here the sine will cancel with that sign. So I'm going to have only cosine x. Now our objective was to make a transformation of this statement into cosine only. And I do have a couple of cosines here. And I'm also seeing second power. Whenever you see second power, you should immediately think of the Pythagorean identities. And so we could re-express sine squared as 1 minus cosine squared. So I'm going to substitute this in for this part of my expression here. And now the entire expression is rewritten as cosine only. So I've accomplished the goal in one sense, in that I have a completely reorganized statement that's only cosine. However, we can simplify some more. Because of the fraction, I can take 1 divided by cosine and minus cosine squared x divided by cosine. So I'm using the distributive law on this fraction here and separating that. Plus I have this extra cosine term here. And this is going to simplify. So I'll have 1 over cosine x. The cosines cancel. Plus a cosine. And so ultimately, this is going to simplify down to 1 over cosine x. So that extremely complicated statement that we started out with in the beginning, it did transform into cosine only. In fact, it transformed into a 1 over cosine. So these are examples of powerful skills that you can accomplish with a little bit of algebra and knowing identities. You can take some hard things and simplify them into much easier things. Well, here's another one to simplify. Cosine of theta plus h minus cosine over h. You might recognize it. That looks like the difference quotient problems we did back in the early part of the course with algebra. We didn't do any of these difference quotients with trigonometric expressions, but this is something you should be able to simplify. And also notice the cosine theta plus h. That's an angle plus an angle. There are identities for that. Those are the angle sum and angle difference identities. Cosine of an angle plus an angle. So I encourage you to use that identity and write down that problem and give it a try and solve it first, and then come back after you've paused and tried that. All right, so I have been doing office hours while I'm recording this presentation, so I stopped to meet with a student and drop by my office hour. in Zoom, but so I forgot where we left off here, but I'm hoping that I told you to solve it by yourself. And now let's do that. Let's simplify this. So we do have an angle plus an angle, and that we can simplify if we use the angle sum identity for cosine. So that's going to equal cosine theta, cosine h, minus sine theta, sine h, and then that is minus cosine theta. All this is over h. So really, the main thing we can do to this is the angle sum identity here. However, when you're in calculus, you'll want to play around with this a little bit more and see how h changes the whole story. And so simplifying this is handy. So what I'm going to do is take these cosine terms and simplify them. So let's factor the cosine of theta. And when I factor out of this, I'll have cosine h. And when I factor cosine out of negative cosine, I'll have a minus 1. And on this one, I can't really do too much to factor that. Sine theta, sine h. And all of this is divided by h. So it turns out in calculus, when you're dealing with this trig and this algebra, you will make two fractions here and divide this one by h. And then this one, we'll just use the distributive law here. We'll have sine theta, sine h. We'll divide this by h. And so it'll be a very interesting conversation in calculus to study what happens when h gets really small. But as far as trig goes, this was really the main thing that we could do with that as far as simplifying it. Or it's not so much simplifying it, but reorganizing it. And so this difference quotient, if it's reorganized like in this form, it can be studied in calculus and give some interesting and unique outcomes. All right, there was one more identity that maybe we should practice. I'll do a real quick one here with the double angle identities. Here's one last one for you on simplifying identities. And you're going to be asked to simplify this statement. And I'll challenge you again to pause and see if you can simplify it yourself. All right, let's give it a shot. See if you can, how you did. And hopefully you looked at it and says, does that look familiar? Does that look like anything we've seen before? And the configuration of this, of a sine times a cosine, we have seen something similar to that. 2 sine theta, cosine theta. The configuration of this identity is close, but not exactly to that. But having the sine cosine is the double identity, double angle sine of 2 theta. Okay, so but this expression that we're dealing with doesn't fit the configuration of this perfectly, because this has a 4, not a 2. And this has these 8 x's in it, not thetas in them. So we got to do a little bit of adjustment here. And we could say, well, let's factor a 2 out. And so we'll have 2 sine 8x cosine 8x. And now I'm starting to see the configuration of my identity matching more with the double angle, the 2, the sine, and the cosine. But this 8x here, that's kind of not quite working. But what if we temporarily, now a lot of you could do this in your head, but just for clarity for some people that aren't quite seeing it all, let's set theta equal to the 8x. That means I can take this out. And so this will equal 2 sine of cosine of thetas. I'm taking the 8x, just replacing them temporarily with theta so you can kind of see, wow, this now is arranged in a way that exactly fits the configuration of the double angle identity. So I can substitute out this whole thing with the double angle identity. And so I'm going to have 2, and then I'm going to have the sine of 2 theta. And that was just a temporary measure for me in my mind to simplify this, to see the correlation between the identity and the double angle. And so I don't really want it to be about theta, I want it to be about x, but theta is 8x, so I'm going to plug that back in here. And so this will equal 2 sine of 2 times the 8x. And in the end, this will be 2 sine of 16x. 16x is the double angle of 8x. And so this expression is an equivalent, oops, I said oops because I was thinking about the cosine double angles. The cosine double angles have a lot of squares in them. But this is, we're right on track for the sine of 2 theta. So sine of 2 theta, 16x is the double angle of 8x. So it's going to decompose into this smaller statement here. Anyways, there are several examples of transforming identities, and hopefully that was good practice for you. Let's go next to solving some equations of trigonometric equations. Here's an example of a really simple trig equation to get us started. Now, the simple trig equations and the hard ones have the same basic plan. You simplify the hard ones down to an isolated trig equation. Once you get this basic isolated trig equation, you first of all find your angle, find your theta quadrants. And you can use the A-Smart Trig class to figure out how many solutions there are. And typically there's 2 solutions because, like in this case, it's negative, cosine is negative in quadrants 2 and 3. Next, you find your reference angle. Find the reference angle. You can solve for the reference angle quite easily. And you do it by forcing the equation to be positive. This is a pretty reliable way to find all your solutions. Get that reference angle first, because the sine and the cosine and tangent inverse functions don't have a consistent outcome every time, because they have domain restrictions and they limit you to different quadrants. But you can't find all your quadrants with the inverse trig function. But you can always reliably find the reference angle with all of the inverse trig functions. But it does have to be positive in order to do that. And then the third step is you find the true theta from the reference angle. All right, so for example, on this problem, if we were to look at cosine, it equals negative. Okay, cosine is negative in quadrants 2 and 3. So we have 2 solutions that we're going to try to find. We also have to make sure we're in degree mode, and we're going to change the problem. Now, some of you may not write this down, but I'm going to write it down for emphasis. I'm switching the problem to be a positive because I want to find the reference angle. And so now that I have a positive equation, I can do the inverse cosine. And I'm just putting the positive now for emphasis, but that's going to give me my inverse cosine of that positive ratio, and it will tell me the reference angle. So if we pop that in here real quick, cosine inverse of 0.85, 0.85, keep missing that. And we get 31.8 degrees. Let's just round it off to tenths. So the reference angle is 31.8. And now we can go for the true solutions because we know there's one in quadrant 2, another one in quadrant 3, and so theta will equal 180 minus the reference angle. And in quadrant 3, it'll be 180 plus the reference angle. And so we can pop those out in our calculator quickly too. So 180 minus, here's my reference angle, enter that, and I got 148.2, and then I'm going to repeat that equation, but I'm going to change it to plus. And I got 211.8. So there are my solutions to that simple equation. All right, let's look at some harder ones now. All right, so here's a new one for you to solve. This one's quadratic though, so it's a big step up compared to the last problem. So pause and see if you can solve it by yourself. All right, let's give it a shot. See how it checks out for you. It is quadratic, so I need it to equal 0. So let's move some things around. Excuse me, move some things around here. I'm going to add that over. Minus the 3. I got it equal to 0 now, and I hope it factors. If it doesn't factor, we can also solve it by the quadratic formula. So I've got to have 3 and 1 for the 8. Let's go 4 cosine times 2 cosine. That gives me my 8. 6. I need a positive and a minus. So that gives me 6 cosine minus 4. I'm thinking it out myself right now, and I got 2. That works. So I got it factored. And so now that it's factorable, I've got 2 factors I can solve for 0. 4 cosine theta plus 3 equals 0, or 2 cosine theta minus 1 equals 0. Now on this one, I can subtract by 3 and divide by 4. And I get negative 3/4. Or this one here, I can add the 1, and I get cosine theta is 1/2. Now this one, cosine of theta equals 1/2 has exact answers. Cosine of negative 3/4, it is solvable. 3/4 is less than negative, it's between 1 and negative 1. It's in the proper range. This has 2 answers. They're just not nice answers. This one has 2 answers that are nice. And so let's do this one really quick, the cosine half, because that's based on exact values that we've memorized. Cosine is positive in 1 and 4. So in quadrant 1, my solution is just the reference angle, which has to be in, let's do this one in radians. I didn't indicate. If you solved it in degrees, then that's fine. But I'm going to practice it out in radians. So we're going to solve from 0 to 2 pi. So cosine of 60, which is pi thirds. That's one of my solutions. But there's a second solution over here for cosine to be positive 1/2 in quadrant 4, and that's going to be 2 pi minus the pi thirds. And so that's 8, that's 7 pi, no, not 8, that's 6, that's 5 pi thirds. All right, so this one, I'm hoping that one's straightforward for you because it's based on memory facts. This one is not based on memory facts. We're going to use the calculator for it. Now, it is negative. Cosine is negative in quadrants 2 and 3, and I'm going to change this problem to be positive because I want to find the reference angle. Now I'm forcing it to be positive, and it's going to tell me the reference angle when I do that. And so the rest is a lot of calculator work here. But we do need to switch to the radian mode. And so, got that covered. Not yet. Cosine inverse of 3/4. And we get 2.7227. Now on paper, I'm just going to round it off. This is a round off here, and this is a worse round off. But just for laziness in writing, I'm not going to write down the whole thing. Now I'm going to find the true solutions. Well, they are in quadrant 2. So theta is equal to pi minus the reference angle. And quadrant 3, theta is equal to pi plus the reference angle. So I'm going to use this more exact answer to do my next calculations and then round off from here, not from here. I'm not going to use this round off in here to give me a round off error. But let's see, pi minus the reference angle, and that's 2.4189. 2.4189. And then we'll repeat that process, this time with an adding. And we'll get 3.8643. There's our two solutions. But we actually have 4 solutions. These happen to be exact fractions of pi, where these are fractions of pi, they're just not very nice fractions, and so we just resort to using the decimal value. Now, if you had doubts about this, are there really 4 solutions? You could graph it and check your work. So we could, it's clear. So you can see here that I typed in the equation 8 times cosine x squared plus 2 cosine x minus 3. So that's my original, not the original equation, but the equation that equals 0. And I'm going to solve this graphically by solving for the zeros. And I set the window to be 0 to 2 pi and -5 to 5. Now I don't need to worry about the range too much because I'm looking for zeros. So I just needed to see the y-axis, the x-axis really well. And now I'm going to graph, and I see the graph, and it has a 0, second 0, a third 0, and a fourth 0. So algebraically, I found 4 zeros, and that's confirming the 4 zeros I found here in my algebra. And if I wanted to get more precise here, we could actually come in here and find these values. So let's see, this is quadrant 1, quadrant 2 is that one right there. Let's see if it matches this number here. So we can go second calc, find the 0, And I'm going to go to the one I'm interested in. I'm not going to find them all, but I'm just saying I'm interested in that one. I'm going to set a left boundary marker, enter, go right past it, put a right boundary marker and hit enter, and it found 2.4189 same. So I've got graphing solution matches my algebraic solution. So now I have a lot of confidence that this one is good, and likely they're all good. All right, so this is examples of solving equations with trig expressions. I got one more equation for you. It's a little harder. 6 sine of 2t plus 9 times sine of t. And this one's a challenge because one is we need to isolate sine. But here's the sine of t and here's the sine of 2t. So our inputs don't agree on this equation. So there's a challenge for you here. So you're going to have to do something with this 2t, and that's a hint. Why don't you pause and think about it, give it a shot, and try to solve this. Well, let's see how it should play out. So this was the problem we were mentioning, or I was mentioning, and I'm going to rewrite that as 2 sine t cosine t. So I'm using an identity to make this equation better. So at least now all of the angles are single angles, single t on all of my trig functions. Okay, so I just put the parentheses here for emphasis of this identity substitution here, but that's going to be 12 sine t cosine t 9 sine t equals 0. I'm thinking, how am I going to solve this? This has got another whammy in it because now I have a sine function and a cosine function. So now it's gotten harder in that sense. The angle part is better, but now I've got two trig functions. But fortunately, these are products here, and that means it's factorable. I can factor by 3 on the 9 and the 12, and I can factor by sine on both terms. So that's what I'm going to do. I'm going to factor out 3 sine t, and that'll be 4 cosine t. Factor out of 3 sine t, that's going to be plus 3, equals 0. All right, now because it's factored, I have a product. And since I have a group times a group equals 0, that's going to only happen if this group equals 0 or that group equals 0. So I can make two equations out of these factors. 3 sine t can equal 0, or 4 cosine t plus 3 equals 0. So if I divide by 3, all I have to do is solve for sine of t equals 0. And if I minus the 3 and divide by 4, I get negative 3/4. Now shoot, that is disappointing. I didn't choose this example well because that equation is a repeat of the one we solved before. This one's going to have two solutions. For cosine, it's going to be negative in second and third quadrant. Sine of t equals 0. That one is a quadrantal angle. And so the zeros don't come up all the time. They only come up on these quadrantal angles. We've got a point like 0, 1, 0, 0, 1, negative 1, 0, and this one, what is that one? That's 0, negative 1. So this solution is going to only happen on one of these quadrantal axis angles. And so sine happens to be the second quadrant. So if we were to solve this one in, well, let's do it in degrees, because I didn't mark this one either, but let's do it in degrees. I'm going to say on 0 to 360. And that'll give us a reason to rethink this one, because then we'll do it in degrees. So in degrees, not theta, I'm solving for t now. My t is going to equal 0 degrees or 180 degrees. On this one, I'm going to do the same strategy as before, but I'm switching to the reference angle for t. And that's going to be a positive ratio. When I'm all done with this, I have to solve it with positive 3/4. So put in positive into the calculator, and when I do, it's going to tell me the reference angle, the quadrant 1 solution. Second quit. So let's change it to degrees. And we'll do the cosine inverse of 3/4 again. But this time we'll get a degree solution. So the reference angle is 41.4 degrees. And so we'll just leave it there at 1 decimal value. And then we can transfer that into quadrant 2 solution and a quadrant 3 solution. The real theta, not the quadrant. Theta, comma. Theta equals, I'm still in radians. Trying to go too fast for my brain, minus the reference angle, and 180 plus the reference angle. So I think we can do that in our heads. 180 minus, I'm not going to do it in my head because I already made some mistakes with mental math, minus this result, and I got 138.6. 138.6, and then we'll repeat it for the quadrant 3, and we're going to get 221.4 degrees. All right, so there we got all of our solutions. And we also could go back and check this one by graphing it to see if there really are 4 solutions. So that's kind of a quick overview or run through of solving a few equations. Next, let's look at some solving of triangle kinds of problems. All right, so here I'm giving you a little section to solve triangles, and this is our first one to start us off. It's similar to a homework problem that we've done, but I've made it a little bit more challenging. And I challenge you right now to pause this video and solve it. There's many paths to solving it, but give it a shot. All right, let's check and see how it went for you. So here's some of the challenges. This little side triangle here, the triangle BCD, I only have one angle. An angle is not enough to solve anything in triangle BCD. Now triangle ABC, I have a side angle side. I can solve everything in triangle ABC. But then I have this large triangle ABD. In triangle ABD, I have angle D, and I have angle A, and I have side AB. So actually I have angle, side in the big triangle. So I could solve BD in the big triangle. I could solve angle B in the big triangle. But I don't have enough information to solve this piece until I solve side AD. Maybe I could subtract. Anyways, there are many, many strategies here. But we're not going to be able to get directly at the x. We're going to have to go indirectly at the x. And so I am thinking if we had triangle BCD, if we had one angle, one more angle, and one side, then we'd have angle, angle, side, and that would be solvable in the small triangle, which means we have to hunt down angle C. This is my plan. And I have to hunt down the side BC. And then I'll have, if I have this angle, then I can get that angle and I can get this side, and I'll be able to solve for side X. So let's start breaking it down and find these two pieces of information here. So just to track down what I have. All right, so just to save some time, I recorded the information that I'm given. Angle A is 47. Side A, I'm using the little triangle here for little a for this side over here. Opposite angle A. And opposite B is, side B is 15. Opposite angle C is side C, which is 13. And I really want this angle C, and I want this side BC, which is side A in my information here. I could find angle B too if I need it, but I don't need all that information. So let's begin with this side A. Now this is side angle side data. That is the law of cosine. So if I want A, I'm going to have to do A squared, B squared, C squared minus 2BC cosine of A squared. I'm going to speed up here. Okay, so you can see I'm using the law of cosine here, and I plugged in all the information. I'm just going to let the calculator crank all this out. 15 squared plus 13 squared minus 2 times 15 times 13 cosine of 47. And that's going to give me A squared, 128.0. And so A equals square root of that. And we'll take this approximately 11.3. So I found one of the sides I need. 11.3. So that is my side right there. That was one milestone in my plan to solving. The next milestone is to figure out angle C. If we had that, we could make some headway. Now, angle C, there's a couple ways. I could use the law of cosine again. And honestly, the law of cosine is safest, because if I use the 11.3 and the 13, I'm doing side-side angle, or angle side-side, which is the ambiguous case. And the ambiguous case can have two solutions. Now we do have something going for us if we feel like if we're safe to do this. It's not always safe to assume from the drawing, but the drawing is acute triangle, and so that's going to help us to find C if we assume that all these angles are acute. So the law of sine can be okay. But if we do side-side angle, we are using the law of sine, which could lead us into an ambiguous case. But I'm not going to make a big deal out of that. And the law of sine is a little easier. We just have to make an assumption here that this is less than 90. And with that assumption, let's solve it. Sine C over side C equals, I'm going to do sine 47 over 11.3. And then this way I can find sine C equals 13 sine of 47 over 11.3, which gives me I'm going to use the exact value right here and put that whole thing on there. And I get 0.84 0, 3. Now I'm going to do the inverse sine of this because that's sine C. I need C and so we'll do the sine inverse. I'm going to use that whole thing in the calculator and I get 57 degrees. Let's call it 57.2 degrees. So technically there's another answer. And we did not study the law of sine very much. The ambiguous case very much. So don't worry about that detail here. But now we have 57 is the other angle that I needed. Okay, so I got all the details on this this triangle here. I'm going to translate that to this other triangle now. And I've got, I think I'll change colors for that. I'm going to call this one C prime because it's the supplement of C. So now we know C prime is 180 minus the 57. No. I'm going to take that whole answer there. It's just a good practice to get the most exact answer and then round off. So I'm going to take 122.8. I also have angle D. It's 41 degrees. And I've got side D, which is 11.3. I think I need the angle opposite x. So that's angle CBD. Let's call that B prime. So this one over here is B prime. And I don't know what that angle is, but I can find it real easy because I have the other two angles in the triangle. So if I do the 180 minus the 41 and minus the 122.8, and we got 16.2. Okay, so the last thing I need is side CD, which we're calling X, which is, well, I'm just going to call it X. And if I get that number, I'll be done. And it looks like we have two angles. Actually, we have all three angles now, so we can do law of sine and find x equals, it's actually x divided by sine of 16.2 degrees equals 11.3 over sine 41 degrees. So x is going to equal 11.3 times sine of 16.2 divided by sine 41 degrees. And the rest now is calculator work. All right, so I just put it in the calculator. You don't have to see me type all that stuff in, and I calculate here. And I'm finding this distance is about 4.8 units. So if these are inches or feet or whatever, I finally found that distance. This is not the only way to solve this problem. There's many paths to get this solution. So anyways, I hope you got that. And if you didn't, double check your solution because your plan may not have been bad and maybe just some math errors. But anyways, think that through. Hopefully that was helpful for you. And I've got a couple more of these solving triangle problems to look at. All right, here is a problem. It's actually from the chapter, the practice problems for the final. It's the one that's focused on the trig equations and trig stuff. So we're looking at a triangle problem that we want to solve. Now I'm going to look at number 11 here. It says the roof of a house has a 20-degree angle. And we've got an 8-foot solar panel. It's mounted on the roof at a 38-degree angle. And we're going to have to put a support bar here to hold the solar panel up on this end. And we need to know its height. Okay, so how can we solve this? Well, one thing better about this problem than the previous problem is we can assume, in fact, not assume, this is a height. It has to be a perpendicular distance. So perpendicular distances do have 90 degrees, which means we can use regular trigonometry here. Opposite, adjacent, and hypotenuse. Now, h is unknown. That's the height of the support. And I can't get that immediately. But this side is opposite the 38. Let's call that y. That is something we can work with. Y is the opposite angle and the hypotenuse. So that's sine. So I can figure out y. This piece here, though, I'm going to have to figure out. And that piece I don't know yet. I'm going to call that piece x. However, this piece x is inside of this triangle here. And so I have this red triangle, and if I knew something about the red triangle, maybe I can solve it. Well, this is the roof, and this is horizontal. And the information says that the roof of the house makes a 20-degree angle. So 20 degrees from horizontal makes the roof angle. Also, these are parallel lines cut by a transversal here. This has to be 20 degrees. So we got plenty of information here if we can just figure out a plan. And our plan, if we solve the red triangle, we'll get x. If we solve for y on the big triangle, we can get that, and then we can subtract x and y, and we'll have h. So there's a 3-step plan right there. Let's solve for this red triangle first. Okay. Well, I'm realizing just now as I speak and as I draw my triangle, we don't have enough information to solve this red triangle. We don't know the slant distance on the roof, and we don't know the base. So let's go back to the drawing board and rethink my plan. I'm going to make a green triangle out of this bigger one. Now the bigger one, we have more information. This is 8. This is 38 degrees, and this is y. That's completely solvable. And so let's get started with that. We know that sine of 38 is going to equal opposite over hypotenuse. So y equals 8 sine 38 degrees, and we're going to have our y calculation here. 4.93. I think these are feet. Yes, they're feet. Okay, so we've got y. Now, I still don't need y ultimately. I need h. And the only way I'm going to get h is to subtract my x. And the only way I'm going to get x is to get more information about the red triangle. But wait, this is the base. And that base on the green triangle is the same base on this triangle. So the red and the green triangles share this same bottom part. Hey, so we can use the green triangle and solve for that value. So let's do that. That'll be our second step here. So if I want the base of this triangle, that is cosine, because that's the adjacent hypotenuse. So cosine 38 is going to equal, I'm going to call it base b over 8. So b will equal 8 cosine of 38. And so that turns out to be, the base number is 6.3 feet. All right, well that's helpful, because now I can come back to this triangle over here, because this base on the big green one is the same base as the one on the red one. So this is 3.8 feet. And now I'm looking for an equation to relate the x that I need with the base and the angle. Well, that's tangent, because I have opposite and adjacent and the angle. So tangent of 20 is going to equal x over 3.8. Multiply 3.8 on both sides. And we got 1.38. And then lastly, we had the understanding that y was equal to h plus x. So all I have to do is find the h by subtracting the y and the x. So I had this y value over here. I just found this x value here. And if I subtract those two things, they're in the calculator here. Here's the y number, and here's the x number. So instead of, I'll put in the more exact values and round off at the end. And I get 3.54. So the height of the pole has to be 3.54 feet. All right, so there's one example of a triangle solution that we solved in the midst of an application problem. I'm going to do one more of these. All right, one more word problem here from the worksheet that we've been working on here. And we've got two tracking stations. They're on a north-south road, so north and south of each other. These are our two tracking stations. And there's a distress signal picked up. It's picked up by a hiker. And so the signal from one of the stations came from a bearing that was south 45 degrees west. Okay, so this station, if they were tracking that bearing of the signal, here's their location, they'd have to go south, and then they'd have to turn 45 degrees west. Okay, so that means that it has to be this station and the signal. This is 45 degrees. Now here's another station. They picked up a signal. If this is their station, they'd have to go north and then turn 20 degrees west. All right, so that would have to correspond to this angle here. Off of the north, I'm pointing north and turning 20 degrees west. Here, I'm off of the south, so I have to point south, turn 45 degrees west. And that's all we got as far as the bearings. But we do have one more piece of information. The distance between the two stations is 25 miles. Now, this is completely solvable for us because we have an angle, side, angle. Okay, so how far from the road is the hiker? All right, well, first of all, we're going to have to solve, they want this. This is the distance of the road. Let's call it R. So we've got to find that distance there. Now we can't get that immediately, but we can solve this big outer triangle no problem because we have angle side angle. And also because this is 45, that's a little nicer. The picture isn't drawn to scale too well, but if that's 45, this is an easy triangle to solve once we've got this side. So let's call this side x. And then we can use the law of sine. Angle side angle, law of sine. So if I do x over its opposite angle, which is sine of 20, and that's comparable to 25, the opposite angle. Now we haven't figured out this angle yet, but that's an easy thing to figure out because we know these two angles, 45 and 20, which is 65, and so that is 65, 180 minus 65 is 115 degrees. And so we can do the sine of 115, and this will give us x. So I already ran the values in here, and you can see the final outcome, that side is 9.43 miles. So the hiker is 9.34 miles away from the station. But the hiker doesn't necessarily want to go through the station because that might be thick forest. They want to go to the road, and the closest way to the road is going straight east. So we need this r distance. Well, fortunately, that r distance is in an easy triangle. So we got one more step. Let's make this triangle red. Now, like I said, the picture isn't drawn to scale, but I've got this side x now. I just figured out that's going to be the hypotenuse of the red triangle. Which is 9.34. This is 90 and this is 45. And so we can find r with sine. Sine of 45 degrees equals r over the hypotenuse. Now, if we wanted, we could get the exact answer here. Well, we could get the exact answer for sine of 45, which is 1 over square root of 2. But that's not going to help the hiker too much. The hiker needs to know decimal for miles. So we can just rely on the calculator here. I'm going to take the 9.43 miles, times it by the sine of 45, and we get about 6.67 miles. So this hiker has about 6.67 miles to go to get to the main road. So there you go. That was a combination of solving an obtuse triangle with the law of sine and a right triangle with just regular opposite adjacent hypotenuse. Okay, so we've practiced solving triangles, and now I got one more thing to practice. All right, the last topic I'm going to review with you in this little video on trig stuff here is trig function graphs. I want you to be able to take a graph and create the equation, and I want you to be able to take the equation and create the graph, going both ways here. Let's do a quick review of many of the things that we've learned about these trig functions. I'll make that a capital. So it could be sine, cosine, tangent, but we know that the amplitude is the absolute value of A. And we've learned that we can find the period of our sine wave or cosine wave if we take 2 pi divided by the B number. Now, just as an aside, tangent is different. The period equals pi divided by the B number. This is for tangent and cotangent. That's just a little aside. I'm going to focus right now on graphing sines and cosines. And if you can graph sines and cosines, then you can also graph secants and cosecants by doing the reciprocal of those curves. But there is a couple more things. There is the vertical shift, which corresponds directly to the number d, and the midline. The midline is the central line that the wave bounces back and forth upon, and that's going to also correlate to the d value. So y equals d is going to be the line that is in the middle of the wave. And then lastly is the horizontal shift or the phase shift. And if you have this plus bx plus c formula here, it's not factored. It's x is a term and c is a separate term. There's a little formula that will tell you where the horizontal shift starting place is. It's negative c divided by b. And we learned all that information so that we could use that to take the equation, get the information, draw a graph. Or if we have a graph, we can deduce the information and figure out the a, b, and c's and then write the equation. So, for example, let's say that we have this graph. So I brought over a pretty picture of a graph. That is actually something that's from Newton. You may recognize this type of problem. And so our job is to write the equation of this red graph. So we've got a couple clues. We have a starting point on the cycle that's clearly indicated, and an ending point on the cycle clearly indicated. So we'll use that information to write an equation. So I transferred it over here. Let's see if we can figure this out. So here's my starting point. Pi thirds, negative 1/2, and pi thirds, negative 1/2. And what do we see? Let's start pulling information from the picture. So 1/2, negative 1/2 is right here. 1 is right here, and here's negative 1 and 1/2. And we have a wave kind of trapped in between that window. So that means y equals negative 1 is the midline. All right, so if we have the midline, that's an easy, important clue. Midline. That means we got our d number. So d has to equal negative 1. So that was a fast piece of information directly off the midline. Another thing we have is the amplitude. From the midline up is amplitude. Okay, well that is a height of 1. So the amplitude, I said that wrong. From the midline up is a height of 1/2. So the amplitude is a half. And also we're noticing that what kind of wave is in the box. This is a normal cosine here. There's no reflection. So maybe we should have written that down first, is that we're dealing with cosine. And it's a normal, it's not reflected. And since it's a normal cosine wave, A is positive 1/2. Okay, so we're halfway done. We have 2 of our 4 parameters. Now we just got to figure out the B and the C. Okay, well, there's formulas for the B number and the C number. The B number is tied to the period. So we got a little bit of work to do for the period. Not too much, but we have to find this period. The period is from the start to the finish. So if we're going to find that period, we got to subtract the end. 5 pi sixths minus pi thirds. Well, that is 2 pi thirds. 5 pi 6 minus 2 pi thirds, which is 3 sixths pi. So the period is pi halves. Okay, now that is not B and that is not C, but it is the period. And the period follows a formula 2 pi over B. So if we solve this formula, the period we have from the picture, it's pi halves. The period formula we have, so we set those two equal, and we can solve this thing. So I'm going to multiply by B. So B pi over 2 equals 2 pi, and multiply again by 2 over pi. That reciprocal will cancel everything. And it turns out here the pi's cancel. So B equals 4. Hey, we found our third parameter. We are down to one last thing. The horizontal shift. If we could see the horizontal shift on the picture, we'd know the horizontal shift amount. And then we have a formula for horizontal shift. We could solve for C. And we can see the horizontal shift. It moved off of the y-axis by pi thirds. So the horizontal shift is equal to pi thirds. That we got from the picture. And we also have a formula. I think I'm going to do this in different color though. Pi thirds equals negative C over B. And we've already solved for B. And if we multiply by negative 4, we will have the C number. That all cancels, that cancels. And so negative 4 pi thirds equals the C number. And since we've got the C, the B, the A, and the D, we've got the equation. So we've also established that there's a cosine. Y equals 1/2 cosine of B, which is 4. X. C is minus 4 pi thirds plus D, and D actually is a minus 1. That is the equation of our graph. That is not the only strategy for solving this. If you studied Newton, they had a slightly different strategy that is a factored form of this. And in some ways, the factored form is easier, but a lot of our problems don't come to us in this factored form. So that's kind of the downside of it. But I'm going to leave that alone and let you really think that through and study that one. Also, this video has gotten to be longer than I wanted, so I'm going to wrap it up here. In the practice problems, I have many equations that I ask you to graph, plus there's solutions to those graphs so you can test yourself. And I encourage you to do that. Find some trig functions, graph them, check the solutions, and see if your graphs are right. But I'm going to stop this video here. Hopefully that was a helpful summary of lots of trig stuff to kind of get your mental trig juices going. Study hard, and good luck with this final.